Okay, let's see. So I just put up an announcement for the results of the quiz. Let's see. Average is about 8.75, about 9. Standard deviation is about 3.25. So the average is about a B. Okay. And then what you typically do is you take the average and you add a standard deviation. So that's about 11. Average plus standard deviation is about 11. So that's like the bottom of the A minuses, the top of the B's. And then if you take the average and subtract the standard deviation, that's about 5 or so. I think 5.5. And so that's kind of the bottom of the B's and the top of the C's, sort of, and below that, it's kind of like a C minus. Okay, so that's roughly how the distribution is. Any other questions at the moment? Okay. So let's see. I have to open this thing, right? Go to. Oh no. Oh yeah. Oh no. Okay, here we go. Right. Okay. So let's see. Right. Oh. Let's see. Oh, sorry about that. Wait a second. Oh. Okay. Right. There we go. Okay. So now we have, yeah. Okay. So today, what we want to do is we want to talk a little bit more specifically about probability distributions. And probability distributions are important, for their own right, because they help us understand randomness and numbers, quantities like revenue, costs, customers who come in today versus customers who come in tomorrow. They help us understand randomness. Okay, and so there's actually a big divide. Several ways to categorize probability distributions, but probably the biggest is this discrete versus continuous. Okay, so this week, as an introduction to probability distributions, we're kind of concentrating on this binomial distribution. But what we want to do next week is we want to go to this, what's sometimes called the Gaussian distribution or the normal distribution. It's the bell-shaped curve, and if you think about it, that's, probably one of the most significant or most important models or most important functions, maybe in all of mathematics and mathematical statistics and even physics, that Gaussian normal bell-shaped curve. It's kind of simple. But it's also very, very sophisticated, and so we want to build up to understanding that by starting with the discrete distribution and specifically the binomial distribution. Okay, so last time we kind of went through things pretty quickly, but there's an idea, the concept of a distribution. And then there's really two ways that we look at discrete distributions. One is this PMF, or probability mass function, and oftentimes it is abbreviated with a lowercase p, and it assigns probabilities to the values of a random variable. So it's a little bit abstract here, right? First we have these randomness and we have these events, okay, like heads or tails or two heads, two tails, whatever events. And then we come along and we assign a random variable to those, like count the number of heads. If you roll 2 die, count the sum of the faces. 1 plus 3 is 4. Then, only then, after we have the random variable, do we sort of hook up or connect a a probability distribution to that random variable. Okay, and so now we're talking about the distributions that we connect to random variables, and we're saying that sometimes we view of them in the lowercase probability mass function view, and sometimes we have the CDF view, cumulative distribution function view. And so this is where we typically use a capital letter. And it's always that the random variable is less than or equal to some number. Okay, so those are the two main views of discrete probability distributions. We'll talk about, we just talked about, results, right? So, what's the mean of a random variable? What's the variance of a random variable? And the variance is related to the standard deviation, right? You take the square root of the variance and you get the standard deviation. So we'll be talking about those. Okay? And so when we think about a probability, or in order to sort of get started, right, we have to have events, we have to have random variables, and then we have to assign probabilities to those random variables, right? How likely are you to see a 2? How likely are you to see the value 1? And how likely are you to see the value 0? So again, let's consider the 2 tosses of a coin, right? And here we see that the probability of heads followed by heads is 1/4, right? And so how do we get that, right? In this case, we get it from the definition of probability, right? Like, here are the events, right? We can see that there are only 4 possibilities. Our sample space is 4. We can see that heads happens once out of the 4, and so we get this 0.25. Okay. There's another way that we can get this 1/4. Can anybody think about it, maybe? So we know that the answer is 1/4, or 0.25. And the way that we got it is we said, here's this random variable, it's defined on these events, and so we see that this event, heads happens once out of the 4 times, and so we say that the probability is 1/4. So is there another way that we can get at this 1/4? Other way? So if you think about it, right, we have heads, followed by heads, right? So we have 2 tosses, right? So can anybody sort of see what's going on? It's like not a big deal, or it is. When you analyze these things, you kind of try to break them down into very, very small steps, right? And you try to figure out and make sense of those small steps, right? So what do we have going on, right? We have right? We have a first toss, and then we have a second toss. So there's 1 toss, 2 tosses, 2 events. And when we have these 2 events that happen, like the first toss was heads and the second toss was heads, what are you supposed to think of when you see and in these events for probabilities? Remember last week we talked about and being the what of 2, sorry? Not quite adding them, you're on the right track. When do you add probabilities? You can add probabilities when you want to do what? So, was it last week, Rao? add when do you add probabilities? It's when you have, yeah, or, right? A or B, yeah. A or B. And what was the operation that we associated with that? Or A or B? That's the union, yeah. Okay? So if you have or, that's when you should think about adding probabilities. Okay, so here we don't have heads or heads. We have heads first or heads second. We have heads first and heads second, right? So this time we have and. Okay, and when you have and, what should you think about? Not adding, but multiplying, right? Multiplying. Right? And then instead of the union, it really is the intersection. Okay, multiply probability. So we have, another way to get the same answer is we have heads first, and heads second, right? Probability of heads first and heads second, right? So then we have 1/2 times 1/2 equals 1/4, right? Why? Because these are independent. Okay, remember, really, if you have probability of H1 and H2, you should really do like a probability of H1 times the probability of H2 given H1, right? Or I'm kind of running out of space here. Or you could do the probability of H2 times the probability of H1 given that H2, but they're independent, and so this conditional probability is the same as the total probability, and so that's why we can just get the probability of H1 times the probability of H2, right? So we can just do this multiplication, right? Because they're independent. Okay, does that make sense? So you might say, oh, it's not a big deal because we already know that it's a quarter, but actually, what we want to do soon is we want to say, well, this idea about heads or tails is really this sort of, sometimes people call it a binary event, like either a 1 or a 0. There's only two possible outcomes, like on time, not on time, on budget, not on budget, whether it's, people show up or they don't for banking, right? If you have do any business on credit, right? If you have accounts receivable, what's the likelihood that somebody is going to go in default, right? What's the likelihood that they won't pay? People either pay or not pay, right? Credit cards, bank loans for buying a car, mortgages, and so forth. And so it's either they're current or they're in default, right? They make their payment on time or they make their payment late. Or you could even possibly extend this to have, they just make a few late payments or they really go into total default. But anyway, whenever you have these binary cases, we can actually, which occur quite a bit, that's when we want to start to study them a little bit more, okay? So here, our random variable is that, on 2 tosses of a coin, there's 1 head. So we can go to the definition of probability, right, and say, well, we just count the number of cases where it's 1 head, and there's two of them out of the 4, right? And so we actually have 1/2, okay? And notice that here we're thinking about, we can think of it about, sort of following this way. There really is one way to have heads first followed by tails, and so that's probability of a quarter. And there's only one way to have tails first and heads second, followed, and that's has probability of 1/4. And we're talking about the ways to get one head is either this case, or that case, right? And so if we think of either this case or that case, then we have this or situation where we want to add probabilities. And then, of course, we have to subtract their intersection, but the intersection is the empty set, right? If you flipped heads first and tails second, and then compared to tails first and heads second, there's no way that you could do both. There's no intersection between those. It's either, they're sort of, you either did this case, case, in this case, case 2, you either did case 2, or you did case 3, and there's no way that you could have some combination of both of them, so they are mutually exclusive, right? And so we can just straight add, and you could say we subtract 0, or we can just say, forget about subtracting the intersection because it's 0. Okay, and so the last case is very similar to the first case, right? And so now we add them all. We have sort of the whole probability distribution. Okay. Now what we want to do, right, is we would like to generalize this, because this whole idea about on time or delayed, default or not default, there's a manufacturing defect or there's no manufacturing defect. Those binary cases happen often, but the probability of one or the other is not always a half, right? What's the probability that a flight is delayed versus that it's not delayed? It's not a 50-50 chance that it's delayed or not delayed, right? It's uneven, right? And so in order to generalize this, we need to be able to handle cases where the probability of heads or the probability of tails is not symmetric, is not 50-50, right? And so if we want to go be uneven, then we have to use those, right? So how can we, so now suppose that we have the coin that it's biased, right? And so the case that we did here, we would call the fair coin, where the probability of success, the probability of failure, probably heads or tails is 1/2. They're the same, right? So this is where we need to generalize. Right, so here's where we're going to use independence and this mutually exclusive independence, so we can multiply, and mutually exclusive plus, so we can add. Okay, so that's how we're building on the ideas from last week, right? So now notice that we have the same random variable as before, right? So when we had the fair coin, right, we have this random variable. Now we have the same random variable because it's going to count the number of heads, but now that our underlying process has changed, right, we're saying probability of heads is 1/6. So of course we kind of did this last time, but the probability of tails, right, since it's either or, right, the probability of tails is really 1 minus the probability of heads, right? So that's equal to 1 minus 0.6. So this is the probability of tails is actually 0.4. And you can see that really this can be anything. Like once you set the probability, if it's kind of like default, hopefully your customers will be in default maybe 1% of the time or 0.1% of the time, right? And so then the probability of the other one would be 99% or 99.9%, whatever, 1 minus whatever event you're looking at, right? Because the two probabilities sum to 1. Okay, so if we were doing this case, right, where the probability is equal to 0.6, how would we assign the probability to 2 heads if the probability of heads for one of them is 0.6? How do we do that? Any ideas? So remember in this previous example, right, we looked at the probability of heads first and heads first as being independent events. And so we do assume, assume independent and mutually exclusive. So how do we do this? Sorry? Multiply which by 2? Oh, multiply by 0.6? Is that right? Yeah, okay, right. So really what we have is the case where the random variable equals 2, right? If you go back to the underlying event, right, that's the probability that it was head once, I guess, and heads the second time, right? And so that's actually equal to the probability of H1 intersect H heads on the second one, right? So we're really, and because they're independent, right, we can take the probability of heads times the probability of heads. And here I'm just dropping the fact that it's heads first versus heads second, because the probability that it's heads first and the probability that it's heads second is the same, right? So that's actually equal to 0.6 squared, I suppose we might as well say 0.6 squared, and so that's equal to 0.36, right? Or if you did it with 3/5, it would be like 9/25. Okay, and similarly, what about the probability that heads, that you have one head? And so remember, this is the case where we're flipping 2 coins, or not really coins, but we have some process where the probability of success, say, is 0.6, and the probability of failure is 1 minus that, which is 0.4. So what's the probability of having one of the 2 being successful? So here, it's what's the probability of 2 heads, probability of 2 successes. Here, what's the probability of only 1? Any ideas? 0.6? Well, that's only probability of heads. That's only one probability of heads. So here, the probability of having one head, how could we have one head only? It's got to be what? Right. In order to have one head, right, we have to flip the process is we flip it twice. So the first flip and the second flip. So we cannot, what's the probability of one head? We can't just say it's 0.6, because that's the probability of flipping once and getting a head. Here, we're saying we flipped it twice and we got one head. So the only way to do that is you got heads once and then tails the second time, right? Because if you did heads on the first one, or if you did heads and heads, then that would be, the count would be 2. The value of the random variable, the number of heads would be 2, right? So how can you get 1 head? Well, one of them was heads and the other one was tails. Then for sure your count of the number of heads would be 1, right? Does that make sense? So how do we do that? What's the probability of only 1 head? I guess I should say exactly 1 head on 2 tosses of a coin. And oh, by the way, the coin, we're saying it's well, I guess we shouldn't say coin, right? We have this binary event, manufacturing defect or no manufacturing defect, late or on time, or success or failure, and so the one probability is 0.6, and then the complement of that, the other side of that, is 1 minus that 0.6, which is 0.4. And so now we're doing this, repeating this twice, so two times, and we want to know what's the probability that it comes out just 1. Oh, yes. Okay, you're on the right track. Okay, you're definitely on the right track. So here, again, we sort of, it's a little bit indirect, right? Here we want to basically hook up or assign a distribution. We want to assign probabilities to this random variable now, right? And so remember, the random variable is defined on these events, and so we kind of have to take a step back, right? And we have to say, well, in order for us to figure out what's the probability of 1 head, we have to go back to the events, right? So we have to say maybe that the probability of heads once and so heads on the first throw and tails on the second one. And there's another way that we could do that, right? We could have the probability for tails on the first one and the probability of heads, right, on the second one, right? And so if this one happened, we would have 1 head, right, in the first toss. If this one happened, tails first and then head second, we would have, 1 head on the second one. So what is the relationship of this case to this case? In relationship to this 1, number of heads is 1, right? How can we get where the number of heads is 1? Well, we could have this case, right? That's would count, that would fall under this number of heads is 1. This one also, right, would give us that the number of heads is 1 on 2 tosses or 2 runs of this underlying event of success or failure. Does that make sense? So what's the relationship between this case and that case related to 1? And I'm trying to relate this to these sort of fundamental operations, right? In order for the number of heads to be 1, we could have this one, and what's the relationship between this one and this one as far as the number of heads being, the total number of heads being 1? Is anyone with me? No. So does this satisfy the criteria that number of heads is 1? Yes, right? And what about this one? Does this satisfy the criteria that the number of heads is 1? Yeah. So what about these two cases? We can take this one or that one. Oh, good, thank you. Or that one, right? So how can we get that there's that on two tosses there's one head? We could have this case or this case, right? And so since we have or, what do? We add, thank you, right? So this basically means that we have a probability of heads times the probability of tails plus a probability of tails times a probability of heads. Does that make sense? Okay, so here we're dropping, because we know that they're independent, right? We're dropping things a little bit. And so here this is kind of saying, in order to determine the probability that there's one head on two tosses of a coin, we basically, so it's and heads first and tails second, and or this one is tails first and head second, right? And so because each of these is and, we multiply. Okay, so the and, right, gives us the multiplication over there. And then because we take either this case or that case, this is the plus, right? So this is or. Okay, and then I guess I should do the dot for multiplication. We can multiply because of and intersection. We got heads first and tails second. Or, so we can take heads first and tails second. So how do we get that probability? We can multiply. Or we can take tails first and head second, tails first and head second. And so because of that, we can multiply those. Does that make sense? Okay, and so obviously they're the same. And so we'll just say 2 times the probability of H times the probability of tails, right? Because here, right, technically this is 0.4 times so this is 0.6 times 0.4, and this would be plus 0.4 times 0.6. But whether you multiply 0.4 or 0.6 or 0.6 or 0.4, it doesn't matter, right? So it's basically the same, right? And so this is equal to 2 times 0.6 times 0.4, right? So that's equal to 2 times 2 times 0.24, right? So this equals 0.48, right? I think. Right? Does that make sense? Okay. And so the last one, it's pretty much a mirror of the first one, right? Because we have only the 4 cases, right? And so here we want the probability of tails first, and tails second, right? So this is really the probability of tails and tails, right? Which again is really the probability of tails squared. So that's equal to 0.4 squared, and so that's equal to 0.16. Oops. So sorry, I think this was left over from the other one. So if we do 0.36, and then we'll say 0.16, and then we'll do the 0.48 later. So here we should be adding the 0.36, right? Got it over there, plus the 0.48. We'll do that at the end, plus the 0.16 over there, right? This is equal to the 0.36 and the 0.16, right, together, that's 52. So 0.52 plus 0.48, and then that's clearly 1, right? Because 0.52 plus 0.48, that's just 1. Does that make sense? So we kind of got it. Okay, so now, so let's take a look. So what we want to do is so these two different cases that we've been looking at, these are actually instances of what's called the binomial distribution. Okay, and the binomial distribution. And so we could abbreviate that as BNP, where N is the number of repeats or repeated, I guess we'll say, runs. And then P is equal to the probability of what's generally called success. And then, of course, sometimes people say Q equals 1 minus P is the probability of, failure, where success could be heads, failure could be tails, or the other way around, or whatever you're interested in, whether it's on time or delayed. It's no manufacturing defect versus manufacturing defect, or maybe you want to spot defect, manufacturing defect versus no manufacturing defect. So anytime you have this binary type of an event, on time, not on time, heads, tails, in default or not in default, anytime you have these binary events, clearly there's a probability of 1 and happening, and then the complement is the opposite, 1 minus that probability that's given. And so in this very, very compact notation, we are automatic. As soon as you talk about the binomial distribution, you're instantly talking about this underlying experiment, the coin toss, heads or tails, and you're talking about repeating that a certain number of times. Okay, so what we've actually looked at is we've actually looked at two different binomial distributions. Okay, so the first one would be B2.5. Okay, and so what do we mean by B2.5? We mean that, anyone know which one this is? The B2.5? What example was this? This was the fair coin, right? Why was that the fair coin? Well, the fair coin example that we've been looking at, right? So B NP, so the first number is N, the number of trials, right? And so when we looked at it, it was 2 tosses, right? So here, this is N is equal to 2, right? Where there's 2 tosses. 2 tosses of a coin, the fair coin, okay? 2 tosses of a coin. So that's what the 2 means in the B2.5, 2, 0.5. That's what the 2 means, okay? And then the 0.5 means that the probability of success was 0.5. So obviously, if the probability of success was 0.5, heads say probability of tails is 1 minus that. 1 minus 0.5 is 0.5, right? So this is a compact way of saying that so this is the random variable. So it's assigning, 2 to certain events, or 1 to other events, and then 0 to another event. So the random variable assigns values to underlying events. Okay, and then now we can say, well, in this case with the fair coin, we have B to 0.5. On the other hand, we still have the same random variable, right? It's either 0, 1, or 2. That the numerical values that the random variable takes are 0, 1, or 2. Now we want to use this to study a different process. Okay, and this process has 2 repeats, 2 experiments. So kind of like the fair coin, 2 tosses of a fair coin, we're doing this underlying thing twice. Except in this case, the underlying process is different than the fair coin, right? And so where the fair coin had probabilities, symmetric probabilities 0.5, 0.5, here it's more general, where the probability of success is 0.6 and the probability of failure is 1 minus that. 1 minus 0.6 is 0.4. So now, actually, I hope you can see, right? If we can do this, we can do anything. Because now, what if the probability of success is only 0.1? Or, the probability of success is 0.9, probability of failure is 0.1. We can handle that, right? We have to do, some thinking about it, but it's possible that we have the capability to do that, right? Also, similarly, if we want to do more trials, we can actually do that, okay? And so that's why we study this binomial distribution, okay? But before we sort of jump in a little bit more, we want to get used to these two views. And again, we mentioned the parable of the elephant, right, and the Indian village in India. And, there's different views. And so sometimes it's helpful to have this probability mass-ish view of the probability distribution. Other times it's useful to think of this cumulative distribution function, right? And so the CDF, this is the one where we have this probability that the random variable is less than or equal to some value, right? And so here, suppose you have any number less than 0, the cumulative distribution function is 0. And so it's actually what people would call a step function, right? So it sort of has this level value, CDF, cumulative distribution function, has this level value, and then suddenly it jumps up, right? And once it jumps up, it has a steady, like a step, it has a steady value to some other number, and then once you hit that number, it jumps up, and then once you have that value, it stays there for some time, and then it jumps up again, and then in this case, that's it. It's over. It's always going to stay at 1. So this CDF view, cumulative distribution function, the domain, it really could be anything, any number, negative to positive, although it might only make sense to be on the 0 positive anyway. And the probability, the range, the y-axis, it really goes to a few values, but it's between 0 and 1, inclusive. Okay? And so this tells you, what's the cumulative probability, cumulative, so less than or equal to. So it's always stepping, it always either stays flat or increases. So it's as you go to the right, as you move on positive moving x, it always either stays flat or it jumps up. It's always flat. It never goes down. Never goes down. It's always either flat or increasing. So here, kind of at the jump, you could say it's like a jump increase as opposed to like a linear or some other sort of continuous increase. It jumps up or it stays flat. Here, the probability mass function, most of the places it's 0, except only at certain places it has like mass of probability, like there's a bunch of probability and then nothing, and then there's suddenly 50%, which is kind of big as far as probabilities. It's this big jump, and then nothing, and then here's this big jump. And so what I was trying to do is trying to give you the fair coin view. So this is what the fair coin view looks like. From the probability mass function, it's 0.25. So this is symmetric, okay? And then it kind of has a small jump, and then a big 50% jump from 0.25 to 0.75, this big jump in the middle, and then a sort of symmetric jump at the end. And so it kind of looks like that, or it does look like that. So these would be the fair coin. And if you compare, so you can just look at the 0.6 view, you can see that this probability, right, if you compare, right, so the probability that you have 0 is down. So you could imagine starting with this one, say, and pushing down on that one, right? And then here we know it's 0.48, right? So you even take this other one and you push down on that one, So you push those down, and then what happens to the other one? It pops up, right? So you push down on the first one quite a bit, push down on the second one a tiny bit, and then that pops the last one up a little bit. Okay, and so what happens, so this jump is a little bit smaller compared to that one. The next jump, so remember this one by 1, this other one was up at 0.75. Here it's up at, must be 0.64, right? 0.16 plus 0.48 is 0.64, so that's a little bit less than 0.75, right? So, and then it jumps up the most at the end. No, sorry, it doesn't jump. This is the biggest jump, right? But it's got a bigger jump than this other one. So this is just a 0.25 jump. Here it's a 0.36 jump. 0.36 jump. Does that make sense? So here it's like a jump. It's more like a symmetric one, like a little jump, a big jump, and then a little one. Here it's a tiny jump, a big one, and then maybe a middle-sized jump up there. So the CDF matches the probability mass function. Does that make sense? Okay, so these are actually the beginning of the binomial distribution. Okay, so now suppose that we toss this bias coin 3 times. We've looked at the fair coin 3 times, and so the outcomes, the events are the same, right? As we've looked at before, and even the values of the random variable are the same, right? There's either no heads, there's either 1 head, right? There's either 2 heads, right? Or all 3 of them were heads, right? And so similarly, we can do the same thing, where here, though, we can no longer do the traditional approach from the definition of probability, where we take the number of those divided by the number of those, right? Why? Because all of these were equally likely, right? So we can count up the number of occurrences as long as they're only equally likely. So that's how we can get away with this way. If we want to go to the asymmetric probabilities, where it's not 50-50, this is where we need to understand all this stuff about independence, meaning you can multiply probabilities, and then they're mutually exclusive, so you can just add up the probabilities, right? Because here, for the case where there's 3 heads, there's only 1 underlying event, right? So just multiply those together. Similarly, for the case where there's no heads, there's really only 1 event out of the 8 possible events, and so we know that we can just multiply those probabilities. So if it's 0.6 that you have heads and 0.4 that you have tails, it's sort of, so 0.05 is equal to 1 out of 20, or no, sorry, 1 out of 20, right? And so this is almost like 1 in 20. Like if you take 3 tosses of a coin, if you do that 20 times, right? So overall that's 60 tosses total, right? But if you consider this experiment where you're only tossing 3 coins, 1 out of 20 of those times would you really get tails, tails, tails. Okay, it's kind of unlikely. Here, that you only have 1, it's 0.28. Here, it's almost 0.5, where you have 2 heads and a tail. And then here, this is like 1 out of 5, right? 0.2, right? 0.2 is equal to 1 out of 5. So because the heads is 0.6, it's a little bit more likely. You're really a little bit more likely to get 3 heads. Probably, between 3 heads and 2 heads, between 2 and 3 heads, this is like over 50%. So you're really more likely. So you can see how it kind of makes sense, makes intuitive sense, right? So anyway, how do you assign those probabilities, right? Because it's and, you've got heads on the first one and heads on the second one and heads on the third one, we can multiply those together. Okay. Then on the case where, or cases where we're counting, looking for 2 heads out of the run of 3, we have union, right? You could have heads first, head second, and then tails, or you could have heads first and then tails, and then heads at the end, or you could have 1 tail first, and then your second 2 better be heads in a row, 2 in a row after that. So either of these cases, either this one or that one, or that one, right? They all roll up to 2 heads. Okay, so that's how we can add them together. Okay, this one or that one or that one. But then within each case, so now we're saying this case is heads first and heads second and tails third. Here it's heads first and tails second and heads third, so we multiply them, right? And tails first and heads second and heads third, so we multiply them together, and then they're all independent, right? So we don't have to worry about conditioning, given that this was first, given that that was second, given whatever, because they're independent, we can just multiply the straight probability. Okay, so that's how we're kind of bringing in ideas from last time. And so, oh, by the way, it doesn't matter whether you do 3/5 times 3/5 times 2/5, or right, because it's all multiplication, they all have the same value. So we're rolling up to 3 of the 3 times where you have this 0.6 times 0.6 times 0.4 in any of those orders. Okay. So I guess here, this is sort of the CDF view, the cumulative distribution function view. And so I guess technically it would be better to start at the bottom, where what's the probability that it's less than or equal to 0. So again, we sort of did that. Here, this is sort of a mirror of the one that we just did, where here we have only 1 head, so 2 tails, right, in a run of 3. If we're looking at only 1 head, that obviously means there's 2 tails. And so instead of being 2 heads, basically we have 2 tails. And so it's not surprising that we have the same events, but or mirror events, but because of the asymmetry in the 0.3, the 3/5 0.6 or the 2/5 0.4, we're actually coming out with a slightly different number. So we still have 3 of them, but it's now, instead of 2.6s and a 0.4, it's 1.4, 1.6 and 2.4s. So that's why it's a little bit smaller. Okay. And so the raw probability is 0.288. So this would be like the probability mass function. But to have the cumulative distribution function sort of in this column, this is where we add them up starting from the smallest one. And so we have these 2. And so this is building up from 0 to 0.06. Then we add that together. Now we bring in this current one. And then finally, we bring in the last one, right, 0.98. We bring in this last one, and then we have 1. So they all sum to 1. So you can see how this CDF is building up, building up, building up, right? I think, yeah, okay. Okay, does that make sense? So that's kind of the basics for understanding at least this binomial distribution, which is one example of a discrete probability distribution. So as soon as we talk about probability distributions, people want to understand, the center or the expected value. So what do you expect? And then people also want to understand the spread, or what's called the variance or standard deviation of a distribution, right? So, if we look at these numbers, right, 1, 2, 0, 1, 3, 1, 2, Suppose that they're from, a quiz or something like that. Maybe somebody was sick, so they didn't take it, right? And maybe it's just out of 3 or 4 or something like that, maybe out of 3. What's the first statistic or numerical summary that anyone wants to know? Everybody wants to know what? The average, right? What does the average tell you? What does the average tell you? Yeah, so it tells you, sort of most likely. In some sense, it gives you an idea of the middle, right? And the middle, we sort of grade with maybe a B, B plus, say. Right? So we sort of condense all of this variation, all of these scores, all of these, in a certain sense, it's almost not quite random, but, you could almost look at it as, some random number, some process number, right? But of this collection of numbers, what's the middle one, right? What's the average? And then as soon as people hear the average, what do they want to know, right? Sometimes they would like to know the minimum score and the max score, the minimum or the maximum, right? And what do those tell you, right? Those tell you something about the spread, right? And so there's this other one called the standard deviation. And this other one actually called the variance. Okay, and so these give you, so when you see a distribution or a bunch of numbers, a lot of times the first thing people want to know, well, what's the average, what's the expected value, and then something about the spread, like either this min max is sometimes called the range. Okay, what's the spread? The standard deviation and the variance, they also give you some measure of the spread, range. Okay. So, how do we calculate this mean, right? What we can do, right, is to get the mean or the average. What do? We basically add them all up and we divide by the number that were there, right? That's usually what people do. Okay. But if you think about it, right, does it matter if you're adding up a bunch of numbers? Does it matter if you start out with 1 and then you add 2 and then you add 0, right? The order of addition doesn't matter. Right? So if we go ahead and sort the numbers before we add them up, it doesn't matter, right? Whether we add them up in this order and then divide by 8, or we add them up in this order and then divide by 8, it doesn't matter, right? So one thing we could do is we could say do 0 over 8, right, plus 1 over 8, plus 1 over 8, 1 over 8, right, again, plus 2 over 8, plus 2 8, plus 2 over 8, right, and finally plus 3 over 8. So if we, add all of these up and then divide by 8, we could say divide by 8 first, right? We could say 0/8 plus 1/8 plus 1/8 plus 1/8, so got 3 of those, and then plus 2/8 plus 2/8 plus 2/8, so got 3 of those, and then plus the last 3/8, that will give us the same number also, right? That will give us the same number also, right? And so you know, here we say, oh, this is repeated, you know, oh, this is repeated, right? So we could actually say equals, oops. Let's see, how do I make this go away? Oh, there, okay. Okay, or we could say 0 times 1/8 plus 0 times 0/8, maybe, plus 3 times 1/8 plus factor out, right? 3 times 2/8 plus 1 times 3/8. Right? So, actually, right, we oh yeah, sorry. This no, yeah. Sorry. I got a little mixed up. Sorry. This should be 1, and this should be 3, and this should be 2, and this should be 3. Oh yeah. Sorry, I got mixed up. And this should be 3, and this should be 1. We have to divide it a little bit differently. And what am I talking about? What am I saying? Right? I'm saying this because these are actually the values. Like this is a value, this is a value, this is a value, and that's a value. So, right, like if we look back at our observations, or we look back at our data, the data actually runs from 0, 1, 2, and 3, right? And so this is another way of getting the average. Okay, this is called the weighted average. Okay, and numerically or mathematically, right, this is the same as this, right? But this goes through the value 0. Oh, actually, sorry, this should be 1, right? So the value 0, we had one of those. So 1 out of the 8 was 0. Okay, and so we know it comes out to be 0, right? Another value that we had, that, you know, the values of the random variable, right? Another value in our data is 1. And that happened 3 times, and then we, you know, we're always sort of dividing by this 8, right? Meanwhile, the value 2 happened 3 times, and then we divide by 8. And then the last highest value happened 1 time, just like the 0 happened 1 time, right? And so when you take the possible outcomes, so really it's sort of, we're adding up the possible times the probability. That's the weighted average. Okay, and so basically so basically if you look to the next page, what we're saying is that the mean, we also, or average, we also call the expected value. So we have this notation, the expected value of a random variable x, right, is actually equal to the possible outcomes times the likelihood, or times its probability. Okay, and so this is what we call the mean. This is what we call the average. And it looks very different from what we're used to as the average, right? If I say, okay, let's calculate the average, what you would do is say, okay, let's look at these values, right? We add them all up, and we divide by the number that we added up. We divide by the possibilities, okay? So anytime you divide by the number of possibilities, there's a probability lurking there, right? So, I mean, when we talk about average and you add up the scores, you add them all up, you count how many there were, and then you divide by the number that you had, right? That's what you think of as an average. You probably don't think of this as an average, right? Where you take the values and then you multiply by the probability, okay? But that is an average. Okay, so the point of this little exercise, right? The point of this exercise is to convince you that even though it looks different, like we take the possible value, right? So the possible value is 0, and we multiply by its probability, by how often it happened in the data. This other one, how often it happened in the data, probability. This one times its probability in the data. It actually is the same as average. Okay, but since we're dealing with probability distribution, we have these probabilities. Okay, and so anyway, when we talk about the mean of the random variable, the mean of the distribution, this is how we calculate it for a discrete probability distribution. Okay, and so here it is again, right, where the value 0 happened 1 out of 8 times. The value 1 happened 3 out of the 8 times. The value 2 happened 2 out of the 8. 3 also happened 3 out of the 8 times. And then the value 3 happened similarly to the 0, 1 out of the 8 times. Okay, and so if we multiply by its probability, then we get its expected value, average. Okay, so that's sort of the first question that you want to know about any distribution. What's the average? Next, you want to know how spread out is it? And so, how could you evaluate how spread out it is? This looks kind of intimidating, a little bit scary, but here we're just dividing by the number of occurrences, 8, and then for each piece of data, what we want to do is you want to take its value minus the average. Okay, and so what this does, is, in some sense, is this gives us a delta, if you will. This gives us a delta, or a departure, or difference. So how, and remember, what we're looking for is we're looking for some way to understand the spread. How spread out is it? And so, well, the spread is defined from the middle, right? And so how spread out is it from the middle? So we have to make, or we want to understand the spread relative to the middle. So actually, to calculate the standard deviation or variance, it's a two-step process. Number one, you have to actually calculate the average. You actually have to do the mean first. Once you have this average, or once you have this mean or expected value first, then you go back and you have to touch each data, like what's its spread, 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 right? So obviously we have some repeated values, so those spreads are going to be the same, right? And so if we multiply that out, we come up with 0.75, okay? And then that's the variance. And so the standard deviation, so this would be the variance. And this is the standard deviation. Okay, so sometimes we do SD equals standard deviation. So the standard deviation is equal to the square root of the variance. So the variance, sometimes we abbreviate the variance as var. We abbreviate the standard deviation as SD. So the standard deviation is just the square root of the variance. Okay, and so typically we want to look at the mean and one standard deviation, and the mean versus two, so the mean and then one standard deviation up, and the mean and one standard deviation down. Okay, so in this case, for those few scores, right, 1, 0. So here, this is a graph, kind of called the histogram sometimes. So the value 0 we had once, the value 1 we had 3 times, the value 2 we also had 3 times, and the value 3 we had once. So our data over here, right, we could say graph it in this histogram, right? So again, the value 0 we had once, the value 1 we had 3 times, the value 2 we also had 3 times frequency, and the value 3 we had once. Okay, so when we calculate the average, the mean, it comes out to be 1.5, which lo and behold is in the middle. Okay, and then if we calculate the standard deviation, the variance, and then the standard deviation, it's 0.86, and so the mean and one standard deviation is about here, and the mean less one standard deviation is about here. And so if this were a quiz, you might say assign 1A, 3 B's, 3 C's, and 1 D in this case, right? If it really were, say, this spread. And so really, so this kind of shows you how the mean and the standard deviation sort of relate to the center, and meaning the mean, the average expected value meaning the center. Okay, and then how does a standard deviation relate to the spread? How far spread out is it? Does that make sense? Kind of? Okay. So here we already sort of looked at this as a summary for the average. So again, don't be put off by the summation. All it means is it's a process where you add up these things, and so you just have to go through them one by one. Similarly, the variance, it's this process. You have to do it first, you calculate the mean, and then secondly, you go back and you find the difference, you square it so that it's always positive, say, and then you kind of multiply by its probability distribution. You add the number and then you divide by the number of cases. So remember, probability is sort of automatically a fraction. It's automatically dividing by the number of cases, so that's why we don't always see the 1 over n. Instead, it's this sort of weighted average view of the probability. Okay. So now let's see. Very, very quickly. So the very, very last page of this set kind of it shows a page from Wikipedia. Okay. And so this is a whole article they have on probability distribution. Near the bottom of that web page, you might see something like this. This actually is a partial list of the possible probability distributions. Okay, and so we are looking at a discrete univariate with finite support. So this is our friend that we've just been looking at. So this is B and P. Right, and the other one that we'll be looking at would be bounded interval. This one, I think, down here, somewhere here, where this would be the normal or Gaussian. So this is next week. Okay. So these are all probability distributions, and so sort of there was that page that we looked at when we did interest rates. Right, there's like so many interest rates, and we pretend that there's one interest rate, right, for our time value of money. So in our course, we're pretending that there's one discrete probability distribution that we'll study this week, and one continuous distribution that we'll study next week. But really, it's just the tip of the, or not even the tip of the iceberg, right? It's only just the beginning. Okay, and so here is an example that I just want to read through this example. Like, so suppose that you're planning an event and you need 3 helpers. Like, you really need 3 helpers, right? Maybe you're planning a wedding and you need 3 ushers. Pretend, right? Suppose someone else has already picked the helpers for you, but you know that these people have a 50-50 chance of showing up. What's the probability that all 3 show up? And how many would you expect to show up? Okay, and so to help you answer these questions, this is how we actually use the binomial distribution to help you answer questions like that, right? Another one might be, so this is another sort of category problem. Okay, so in order to tackle problems like this, we can use the binomial distribution. Okay, so this is where we're going next. Okay, so we'll see you tomorrow.